In this presentation, I'll be explaining what is meant by active power, reactive power, and apparent powers, and also the concept of power factor. Now, let us see an example to understand the difference between different three powers. Examples to understand the difference between three powers like active power, or that's also called true power, that is represented as P. The unit is watts or kilowatts. Second power is called reactive power, that's represented as Q, and unit is var, that is volt ampere, reactive volt amperes, or kVAR. And the third power is apparent power, that is represented as S, and unit is volt ampere or kilowatt amperes. These are the three powers, and now let us see the difference between all these three types of powers. Now, as an analogous, you see the picture or figure here. Therefore, that is a glass filled with a cocktail represents the true power. That is, there's a cocktail is filled in this glass, and up to this one, this cocktail is there. Therefore, that represents the true or active power. This is the active power representation, that is kilowatt. And the foam on the top is the reactive power, that is the foam that is formed above this cocktail, that is represented, or that's analogous to reactive power, that is kVAR, that is kilo volt reactive volt amperes, kVAR. And the total content of the glass, that is the sum of that cocktail plus the foam, that forms the total size of the glass. Therefore, that represents the apparent power, that is represented as kilovolt amperes. Therefore, this is analogous to that three powers: active power, reactive power, and apparent power. This represents the volume of the cocktail that's inside the glass. That is a useful one. That represents that's a useful power as such. Active power is a useful power. That is represented by this one cocktail, and the form that is above that one, that is reactive power. That is, it's not used one, but that requires us actually. That's not useful power, but that is required. Therefore, the total size of the glass, or that total, that is decided by the sum of these two things. That is that is active power and reactive power. That is the size of the glass. That is the kVA. That is the apparent power. Therefore, actual case in here, if you compare that one in a electrical RL circuit and a AC voltage source is there, and this is a corresponding power triangle in which this represents the active power, and this represents the reactive power, and vectorial sum of these two will represent the apparent power. Therefore, that is P, and this is Q, and this is represented as S. Vectorial sum, that is the total power, or that's called apparent power. Therefore, the size of the glass, that can be considered as the apparent power, and the volume of this form, that is represented as reactive power, and the volume of the cocktail that is inside the glass, that can be considered also analogous to active power. Now, continuing the active or real power or true power in pure resistive circuit. In pure resistive circuit therefore active power is the usable or consumed electrical power in an AC circuit, and has a unit of watts or kilowatt. It's a useful one. Just like as I already told you, in a glass there's a cocktail is there, form is there. For the cocktail, this volume of the cocktail is a useful one. Form is required, but that's not a useful one. Therefore, the summation of this real, that is cocktail volume, that represents the kilowatt, and the reactive one, that's represented by the forms, that is the total volt ampere. Therefore, the true power or the real power is the another form of the active power. Therefore, in this case, in a pure resistive case, the voltage and current, they are in phase. And if you plot that one, this is the voltage and this is the current. And if you do the multiplication of the instantaneous value of the voltage and current, then you will be getting the power. Therefore, this is the third one is the power, and the average value of this one is called the power consumed by the load. That is actually, it is equal to the product of RMS value of the voltage and RMS value of the current. That is the average value of this power, and that is the power consumed by the resistive load. Therefore, in resistive load, voltage and current, they are in phase. And if you compare for a resistive load here, is actually, as I already explained that one, the analogy of a pure resistive circuit is a cocktail. The cocktail is full without forms. That is, if the glass contains full glass is the cocktail without the foam, that can be considered analogous to a pure resistive load. In that case, there is no reactive power as such. There is full real power or active power that represents the apparent power. Therefore, the reactive power equal to 0. In that case, the form, that is analogous case, that is equal to 0. Therefore, here in a pure resistive circuit, real power is the this component will be 0. That's vertical to that one. No, this is a reactive power, that will be 0. So that real power or active power is same as the apparent power. Therefore, the power, this angle is, we call it as power factor angle, and the power factor angle equal to 0 or power factor equal to unity. Therefore, for a resistive circuit, the power factor equal to unity, and as we will be seeing later, the power factor concept. Therefore, anyway, power factor is the ratio of the real power or active power to the apparent power. Therefore, the active power, also called useful power, actually does the real work in the circuit and always flows from the source to load. That is active power. Therefore, in this case, if you consider, if in this glass the full cocktail comes there, then that is a useful one. No, that represents the that corresponds to the active power. That's analogous to the active power. Now continuing the active power and real power or true power in a pure resistive circuit here. As you know that this is the resistive circuit and the voltage as well as current, and if you do the multiplication of the instantaneous voltage and instantaneous current, you will be getting the power, and the average value of the power is the power consumed by the resistance. In that case, it is purely reactive power equal to 0, and therefore active power is given by the equation Vrms into Irms into cos phi, where Vrms is the RMS value of the voltage, Irms is the RMS value of the current, and cos phi, phi is the angle between the voltage and current. Therefore, this is what we call power factor. And reactive power is equal to Q equal to Vrms into Irms into sin phi. Phi is again the angle between voltage and current, or that can also be called as, it is equal to cos phi is nothing but it is the ratio of the active power to the apparent power. For the active power equation is this one, and reactive power equation Q is this one, and Vrms equal to RMS value of the voltage, Irms equal to the RMS value of the current, and phi is the phase angle between the voltage and current. And in pure resistive circuit, phi equal to 0. That is, there is no phase shift between voltage and current. Therefore, phi equal to 0. Therefore, the cos phi equal to 1 and sin phi equal to, of course, 0. Therefore, here real power is given by RMS value of the voltage into RMS value of the current, and the reactive power equal to, since sin phi equal to 0, the reactive power equal to 0. Then apparent power S is equal to the active power. In that case, reactive power equal to 0, and the apparent power is same as the active power in a pure resistive circuit. When the inductive reactive power Q is required, in what condition or what cases the reactive power Q is required? The reactive power can be classified. There are two types of reactive power. One we call it as inductive reactive power. Another one is called capacitive reactive power. Both unit is equal to what? Reactive volt amperes. And the reactive power equation is given by Vrms into Irms into sin phi. This is the reactive power. And inductive reactive power is required by the devices that needs to create magnetic fields and magnetic flux. Those devices which requires to produce the magnetic fields and magnetic flux, that requires the inductive reactive power. And for example, induction motors, transformers, inductors, reactors, etc. These devices requires to produce the magnetic flux or magnetic fields are required. Therefore, in that case, the reactive or that requires inductive reactive power is required in that case, and that reactive power is given by Vrms into Irms into sin phi. Of course, active power is given by P equal to Vrms into Irms into cos phi. Therefore, this is again, as we have seen, is an RL circuit in which the voltage, this is the instantaneous voltage, and as well as the current is also shown here. There's a phase shift is there, that is a phi is the power factor angle, or that is a current is shifted by the voltage by an angle phi. Therefore, this is the instantaneous current and this is the instantaneous voltage. If you do the product of instantaneous voltage and current, then you will be getting the instantaneous power. Therefore, this is the instantaneous power diagram in which this is a positive power, in which that power means that is consumed by the circuit. And what's shown here, the negative power, that is actually the negative power indicates that the inductor is returning energy to the circuit rather than absorbing. Here the energy being absorbed, and here during this period the energy is, of course, that is returning to the circuit, that negative part. Therefore, this is the instantaneous power diagram that is obtained by multiplying the instantaneous voltage and instantaneous current. Of course, current is lagging the voltage by an angle phi, and the power factor angle equal to phi, and the power factor is given by cos phi. Therefore, in RL circuit, the current lags the voltage by an angle phi degrees, and the instantaneous power can be calculated by multiplying the instantaneous voltage and current. That is plotted here. This is the instantaneous power, and the average value of that one is the total average power will be getting. Here this is a positive power, and here negative power indicates that the it is returning. That indicates that it is returning the energy to the circuit. That is, rather than absorbing, it is power is returning that one. That's negative power indicates that. Now continuing the active, reactive, and apparent power in RL circuit. In RL circuit, as we have seen already, resistance is the, inductance is the, AC voltage source is the instantaneous voltage and instantaneous currents are plotted. Product of voltage and current instantaneous value will be getting. That is the power diagram, and this is having a positive power. What is shown in the under this one, this area under this one represents the positive, and this is a negative. Of course, the energy product means this will represent energy product of power and time, that will give the energy positive guys, and this is the negative energy that is given to the return back to the circuit. Therefore, this is a negative energy, and in this is RL, it is the power factor can be. Now, if you looking to that one, it's analogous as I already explained. In a glass, this is a cocktail volume, this is the foam volume. Now, this is representing the kW, and this represents the reactive voltamperes, and the total height of the glass, or that total capacity of the glass, that can be represented as kVA. Now, the power factor is actually the ratio of the, of course, the amount of the cocktail in this one, that divided by the total size of the glass, because that is represent the kW divided by kVA, or it is active power to the apparent power. Therefore, the power factor can be analogous. It can be considered as analogous to the amount of cocktail, that is the amount of cocktail to the size of the glass. How much is the cocktail related to the size of the glass, that represents the power factor, or that is analogous, I'm telling, that is analogous to the power factor of the circuit. Therefore, analogy of RL circuit is a cocktail in a glass with a foam. There's a cocktail is there with a foam is above that one is there, and cocktail is analogous to the active power. This is analogous to the active power, and the foam analogous to the reactive power. This is analogous to the reactive power. Therefore, summation of that one gives the apparent power, and here the power factor is given by the ratio of the active power, of course, the amount of this cocktail divided by the size of glass, or the total of this one, this apparent power, that is represented as the of course, the power factor of the circuit. Same as this one, if you plot that one, this is the active power that is representing by this one, and this is the reactive power that is represented as Q, which is equal to, that is the analogous is the foams that is above the cocktail, and summation of the, it's still vectorial sum, the summation of that one is representing as the apparent power that is represented by the total height of the glass, and the apparent power S, and reactive power Q, and real power equal to P, and cos phi, the power factor is nothing but real power P divided by the apparent power. This and this one is, that is called cos phi. For the power factor cos phi is the active power P divided by apparent power S. And now continuing the active power, reactive power Q, apparent power S, and power in an RL circuit, same circuit here, same as we have seen, voltage and current and power diagram already explained. And this is the power triangle, this is a real power, and this is a reactive power, that is P, Q, and this is the apparent power. Analogously, this is the representing the analogous value, real power, that is the height of the cocktail, actual cocktail, that is a useful power actually. This is a useful power as such, as I'm telling, analogous to the active power. And this is the above that one form is there. That's not useful, but it's required. It is required. That is why the total height of the glass, that represents the apparent power. And the ratio of the active power divided by the apparent power is the power factor. That is the height of the cocktail divided by the height of the glass, total height of the glass. That represents, that gives an idea about the power factor. It's analogous to the power factor, I'm telling. These are all analogous things, just to remember that one. Therefore, the active power is given by P equal to Vrms into Irms into cos phi, and reactive power equal to Q equal to Vrms into Irms into sin pi. Already we have seen. Phi is the power factor angle, or that is the angle between the active power and the apparent power, or we can say it is the angle between instantaneous voltage, the voltage and current. This angle is also called phi. Therefore, Vrms equal to RMS value of the voltage, Irms is the RMS value of the current, and phi is the phase angle between the voltage and current. And in RL circuit, phi is more than 0, of course. Assume that phi equal to 30 degree, the power factor equal to cos 30, which is equal to 0.866. That in the case of inductive circuit, we call it as lagging. So current is lagging the voltage. With reference to voltage, current is lagging. That is why 0.866 lagging. Current is lagging by, the power factor equal to 0.866. And active power is given by Vrms Irms into cos phi, which is equal to into 0.866. Vrms Irms into 0.866. And reactive power is equal to Q into Vrms Irms into sin 30. That was sin 30 times Vrms into Irms. That is the reactive power. Therefore, Q equal to, of course, it is equal to 0.5 Vrms into Irms, and P equal to 0.866 Vrms into Irms. And the total apparent power is given by square root of P square plus Q square. That is actually, this apparent power is equal to the Pythagoras theorem. As per Pythagoras theorem, this are root of P square plus Q square is equal to S. That is the apparent power. And the ratio of the active power, that is P divided by the apparent power, active power divided by apparent power, that is called the power factor of the circuit. Now let us see the conductor size reduction as reactive power reduces and the effect of power factor on the size of the conductor. Now consider this diagram as such. Here, see, this is the conductor. It's a conductor that has to carry both a real power of 100 kilowatt and a reactive power of 100 kVAR. Therefore, that represents the corresponding power factor equal to 0.7 or 70%. Therefore, kVA equal to, if you calculate root of kW plus kVAR square equal to 145. This is the case. Now, what we are doing is, we are reducing the kVAR. Reactive power we are reducing. What happens here? Previously, it was 100. That is reduced to 75 for the same kW. kW is not changing. Same thing, 100 and 100 here. But instead of 100 kVAR, it's reduced to 75. If you reduce the reactive volt amperes, now we see that one, see, kVA now reduced to 125. Power factor is now improved. Power factor is improved. That is real power divided by apparent power. That is improved to 80% or 0.8. Now you see that size of the conductor is now reduced. Again continuing, if there is no reactive power, that is purely resistive circuit, there is no reactive power here to transmit the same amount of power, transmit 100 kilowatt, kVAR equal to 0. Therefore, the power factor is improved to unity or 100%. Now see the size of the conductor. Therefore, the size of the conductor gets reduced as the reactive power to be carried is reduced. In this case, no reactive power is transferring, but here it is 100 kVAR is to be transmitted. Therefore, as more kVAR is to be transmitted, the size of the conductor increases. Another one thing is that as kVAR reduces, we can see that power factor is improving. Therefore, as kVAR, this component is reducing here, you can see that this apparent power is going in this direction, so that the power factor angle gets reduced or power factor is improving. Cos phi is increasing. The maximum value of the power factor, as you know, that it is equal to unity. That happens when the reactive power equal to 0. In that case, the real power is same as the apparent power. Therefore, to transmit the same amount of active power, it is actually 100 kilowatt. It is actually 100 kilowatt. Now, to transmit the same amount of active power, that is 100 kilowatt, size of the conductor can be reduced. That is, the size of the conductor can be reduced if the power factor is improved by reducing the reactive power requirement. That is, the reactive power requirement, if you reduce, the size of the conductor can be reduced and the power factor can be improved. Now, continuing the active, reactive, apparent powers in RC circuit. This is an RC circuit. Previously, we have seen RL circuit. In RC circuit, we can say that instantaneous voltage and this is the instantaneous voltage and instantaneous currents are plotted. And you are taking the multiplication of the voltage and current, then you will be getting the power. This is the power, instantaneous value of the power. You have positive power as well as small negative power is also there. Same, like RL circuit itself, there's a negative power is the energy transfer is the, here positive power represent the energy consumption, and this is the returning of the energy represented. Therefore, here the power factor same as the In this case, the power diagram is like that. Active power is this is a reactive power. The direction is opposite as to the RL circuit compared to RL circuit. Therefore, reactive power, this is the apparent power. And here the power factor angle, which is again the ratio of the active power to the apparent power, P by S. But the thing here is that the power factor, of course, it's a leading power factor. Current is leading the voltage. Here, the current is leading the voltage. That is why it is called the leading power factor is there. For a capacitive circuit, current is leading the voltage by an angle 5 degree. So the power factor is leading in RC circuit. Therefore, the capacitive reactive power often adds to or balance the counteract the interactive reactive power, improves the power factor, and voltage stability can be enhanced. By adding the capacitor, it can supply the reactive power required by the inductor. That is the one application of the capacitor. Therefore, in an RC circuit, you can see that it is a leading power factor. That again, the equation is same as active power divided by the apparent power, and but direction is now reversed here. This is a reactive power, and this is the active power, and this is the apparent power. P divided by S is equal to cos phi. Continuing the same for a RC circuit. Here active power, as we have already seen the equation, Vrms Irms cos phi. Reactive power Q equal to Vrms Irms sin phi. And here phi is the phase angle between that one. In RC circuit, of course, again the phi equal to 30, but the power factor angle is equal to, say, example 30, but it's a leading power factor. Only the thing is that it is leading. And again, you can calculate what is the real power, which is equal to Vrms Irms for 30 degree, cos 0.866, and reactive power equal to Vrms Irms sin 30, same 0.5 Vrms and Irms. But power factor angle is given by, again, same as this, active power divided by the apparent power, and apparent power is given by root of P square plus Q square. For the same as RL circuit, but only difference is that the power factor angle is leading here. Here you can see that one current is leading the voltage. That is why here this is the voltage and the current. Current is leading the voltage by an angle phi. That is by an angle phi, current is leading here. That is why the power factor is leading, and which is nothing but active power divided by the apparent power in terms of looking into the power triangle. This is active power P, and here the direction, unlike the RL, the direction is opposite here. This is a reactive power required, and this is the total apparent power as it here. Now let us see the AC power comparison. This is a pure resistive. This is a power AC power is given to a resistive load. The product, it will be power is being consumed by the resistive load and heat to be produced. And in that case, you can see that voltage and currents are there in phase. Instantaneous voltage and current. If you multiply, you will be getting the power here. What shown here is the power. The area under is it is actually power consumed. That is the energy consumed is equal, not energy actually. The area represents the energy consumed here. And the average power is given by RMS value of the voltage and RMS value of the current. Of course, it is equal to Vm Im divided by 2. Vm by root 2 into Im by root 2. Vm Im divided by 2. This is the average power consumed here. And this is the energy that is during, the energy consumed here, that is represented as this shaded portion here. Here voltage and current, they are in phase. And here there's no reactive power consumed. Only the active power comes here in a pure resistive load. But if you consider the pure inductive leg, here can see that one, here the current and voltage, they are 90 degree apart. If you see that one, the current and voltage, they are 90 degree apart. Here you can see this one, current and voltage, they are 90 degree apart. And if you calculate the instantaneous, of course, power, this is shown as a power. This is the instantaneous power, and this is means that energy is, of course, here energy is released, and here energy is being stored. Here this indicates the energy being stored, and here energy is released. Again, energy is stored, energy is released. Therefore, net energy equals 0. Therefore, average power is 0 in the case of pure inductive load. Average power is equal to 0 because in energy stored, release, energy stored, release, like that. Average power will be 0 in the case of a pure inductive load. And here, of course, that is why there's no active power in this case. Only the reactive power comes here. The third case is the pure capacity. In that case, again, current is leading the voltage by 90 degree. Current is leading the voltage. In that case, again, you can calculate the product of instantaneous voltage and current. And here, it is the energy is stored here. Energy is released. Negative means energy is released, and energy stored is here. That is, now if you take again the average value, same amount of energy released and stored, both are same. Therefore, the average energy, that will be 0, or average power is equal to 0. Therefore, in a pure capacitive case and in a pure inductive case, the average power equals 0. There is no active power involved in the case of pure inductive and pure capacitive case. But here reactive power equals 0, but only the active power comes here. Therefore, this is a pure resistance case, and this is a pure inductance case, and this is a pure capacitance case. Here average power equals 0. Again, here also average power equals 0. Here average power is the active power. Average reactive power equal to 0 in this case. This is the same thing what I already explained, the analogy, AC power analogy as such. It is a glass, a cocktail is kept in the glass, and the height of the cocktail, that is a useful one, that represents the active power, and the foam above that one, that is not useful, but it is necessary also. That is why that represents the reactive power, kVAR, and the summation of that, the total size of the glass, that includes the active power and the reactive power, that represents the total capacity, that is called, volt ampere, kVA. For vectorially, if you see that one, active power and reactive power, they are vectorially added, then you will be getting apparent power, and the ratio of the active power to the apparent power, that is called the power factor of the circuit. That is what this is, an RL circuit in which power factor equal to active power divided by apparent power, P by S. For that, in that case, actually that it is equal to active power means the height of the cocktail divided by the total height of the glass, because that includes this one also. That can represent, that can be analogous to the power factor of the circuit. These are all analogous. Just to understand that one, it is explained like that one. Again, coming to the power factor concept analogy means that here again this is an RL circuit, already AC source, RC circuit. As you already saw, this is the real power and this is apparent, sorry, reactive power. This is apparent power. This ratio of real power to the apparent power is the power factor of, and here also this is the active power, reactive power. This is apparent power. The ratio of the active power, P divided by S, is the power factor of the circuit. And as analogous, we can see that one. See here, as we already seen, this is a glass in which this is a cocktail is there, this is a foam is there. And if power factor is low, means that the amount of cocktail is less and this one is more. Here, foam is more. Therefore, this is, out of the total capacity of the glass, here the amount of cocktail useful one, that is less, for more is the kVAR. This represents the case of a low power factor. But if the foam is less here, that is full glass, almost full glass contains the cocktail, or that case, that indicates that power factor is more here. Therefore, kW is more, kVAR is very less. That indicates the power factor is large, or that is more than 0.9. Just an analogy only, that the reactive power is very less and real power is more. In that case, power factor is more than 0.9. For the power factor, as I already know, it is equal to active power to apparent power, or P by S. Now let us see the power factor for an RL and RC circuit here. It's an RL, simply RL circuit. In RL circuit, here the instantaneous voltage is there and current is lagging the voltage by an angle phi, and the power factor, for the vectorial, it is on that voltage, and this is the current vector. This angle equal to the, of course, the angle by which the current is lagging the voltage. That is same waveform is shown here. This is a circuit asset. And now if you see in terms of the power, or power triangle here, this is the active power and this is the reactive power. Of course, summation of that one, vectorial sum is for apparent power. This angle phi is representing this one, same as that one. Therefore, cos phi is given by, of course, the real power or active power divided by the apparent power. This is the case for a RL circuit. And if you consider an RC circuit, again, the instantaneous voltage is there. Of course, current is leading the voltage by an angle phi. Here, phi an angle phi. And current is leading the voltage by an angle phi. And the RC circuit, in that one, again, the power factor equation is same. Of course, this is a power triangle. This is the active power. That now, instead of going above, it is going down here. And that's it. For the reactive power, this is apparent power. For the ratio of the cos phi, this is angle phi. Cos phi means active power divided by the apparent power. That is called the power factor. In both cases, the equation is same. And here we call it as power factor is lagging. For a reactive or for an inductive case, the power factor is lagging. And here leading, because current is leading the voltage in a RC circuit. Therefore, the power factor is, we call it as power factor is leading. For an RL circuit, current is lagging the voltage by a certain angle phi. Then we call it as power factor is lagging. Therefore, the power factor is lagging for an inductive circuit and it is leading for capacitive circuit. Basic equation for power factor is cos phi equal to active power divided by apparent power, or equal to P by S. Now, as a conclusion, let us see the definitions of power factor. The power factor, a simple and RC RL circuit as shown here. in which this is the instantaneous voltage and instantaneous current of that one, as we already seen. The power factor angle equal to 5. And another representation is that this is a real power and this is a reactive power. This is the apparent power, PQS. And in terms of the impedance, you can say that this is the resistance and this is the reactance and this is the total impedance, root of R square plus X square. This angle equal to again 5. In terms, there are three methods to define the power factor, power factor, in which power factor which is equal to cos phi. If you take this one, it is a cosine of the angle between voltage and current. This angle, it is a angle between voltage and current, cosine of that one, cosine of the angle between voltage and current. That is a one definition for the power factor. Second definition is from the power triangle. In power triangle, it is cos phi equal to the active power divided by the apparent power, which is equal to P divided by S. Third definition is that from the impedance triangle. All are same. Impedance triangle, that is equal to R divided by Z. For power factor, cos phi equal to the resistance divided by the impedance. Therefore, these are the three methods to define the power factor. But this the definition of this one will be different in the case of a non-linear case. This is for a linear circuit. Non-linear case, the definition will be different. In that one, there is let's say what we call it as the total harmonic distortion, harmonics are coming. Therefore, that definition of the power factor will be slightly different in that case. Therefore, in the case of a non-linear circuits here, there will be displacement power factor and the distortion factor. The product of displacement factor and distortion factor will be the total power factor. That is in the case of a non-linear load condition.